Okay, so the last video was about perpendicular bisectors of a segment. This is about bisector of an angle, or the angle bisector. And the angle bisector is just a segment or a line or a ray that cuts through an angle and creates two congruent angles. So here's a little drawing of the angle bisector here. Now the angle bisector theorem states that if you are on the angle bisector, at any point on the angle bisector, is equidistant from the sides of the angle. But the key part of this is that it's equidistant from the sides with respect to being perpendicular from them. So when you have a segment drawn to the side of the angle, it has to be the perpendicular distance. And then the converse says, hey, if your perpendicular distance from the side of an angle is congruent on both sides, you're on the angle bisector. Basically there. Now, the reason this is important then is when we use this theorem on a triangle, which is on the next page of the book. Okay. You have all three angle bisectors. So BP is an angle bisector, AP is an angle bisector, CP is an angle bisector. All three of those cut the angle in half of the triangle that they respectively go through. That gives you a point here, P, for instance, it's equidistant from F and D, from the two sides of this angle. This point is equidistant from the two sides of this angle. So that's why the incenter is equidistant from the sides of the triangle. Again, the perpendicular bisector is equidistant from the endpoints because you're equidistant from the endpoints of the segment. The angle bisector is equidistant from the sides because you're equidistant from the sides of the angle. And that point is called, right here, the incenter. So some examples of that to go through then. Again, I guess kind of run through this real quick. Again, an angle bisector is any special segment, ray, or line that is an angle bisector. Another special segment, ray or line, is an angle bisector which divides an angle into two congruent angles. So, angle bisector theorem says if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Converse just flips it, and then the incenter theorem, the angle bisectors of a triangle intersect at a point called the incenter that is equidistant from the sides of the triangle. Now, in this problem then, we are told that, and it's kind of backwards, they're using the converse for the first problem actually, that EC and EA are congruent, meaning the distance from the side of this segment to the side of this segment are the same. And notice it's perpendicular distance they've given us, not just some kind of congruent segment. So that means this angle must have been bisected, meaning that EBC is 43 and ABE is also 43 degrees. ABC, the full angle, would be 86 because you just add them together. Number two, again, using the converse here really to start off with, we know that this segment is congruent to this segment, and to get its perpendicular distance. So this ray is equidistant from the sides of the angle, meaning that the angle has been bisected. So that means that this angle right here is 47 degrees, YBA, but they want to know, which is what they want to know, YBA. Sorry, I thought they were going to say YBF. 47 degrees. Now, number three, they finally use actually the angle bisector theorem, because these were both, again, converses. Knowing that they're equidistant, that means that the angles are congruent and have been bisected. On number three, they tell us that these angles have been bisected. It's kind of hard to see, but they've both been marked congruent, which means these two segments have to be congruent. So 2x plus 1 has to equal 3x minus 8. Add 8 to both sides, subtract 2x, 9 equals x. Now that's not what's being asked. The question is, what's the length of MK? So now I have to take 9 and plug it back in for K, or MK. 2 times 9 plus 1 is 19. And then for number 4, similarly, just again using the converse instead, this point L is equidistant from the two sides of the angle, again that perpendicular distance. And so now that means that the two angles have to be congruent to each other because it must have been bisected. So 7x plus 5 equals 3x plus 21. Subtract 3x, subtract 5. 4x is 16, divide by 4, x equals 4. And now they know that x equals 4. Okay. plug that back in for really either one of the x's because it's asking for the measure of angle EWL. Well, EWL is just one of the angles. So 7 times 4 plus 5 gives us 28 plus 5, so 33 degrees. Now questions 5, 6, 7, and 8 are working with the incenter. The incenter, point U, which is what they've told us, is equidistant from the sides of the angle, and it also is on the segment that bisects all the angles. So we know that every angle has been bisected in the triangle, and this point is the same distance from all the sides, which is why we can draw that circle on the inside if we want to. So the question is, how long for number 5 is MU? Well, PU is 5, so MU has to also be 5. The question on number 6 is UGM. What's the measure of angle UGM? Well, if this is 28 degrees here, that means UGM also has to be 28 degrees because it's been a bisected angle. So this angle here is congruent to this angle. Number 7, the question is, what's the measure of angle PHU? Well, again, P to H to U is this angle right here, which is congruent to the angle next to it because, again, BH is the angle bisector. So if MHB is 21, PHU is 21 degrees. We're talking about an angle, so degrees. And then number 8. Number 8's a tricky one. We haven't really done any of these, so this is just kind of an extension. But you have to recognize that this guy here is a little right triangle because it's the perpendicular distance. And if I kind of sketch it off to the side, it's 5, 12. Here is HU. So what you're going to have to do to find HU is use the Pythagorean theorem. We'll call this C because it's the hypotenuse. But C squared will equal 5 squared plus 12 squared. C squared is 25 plus 144. C squared is 169. Take your square root. C is 13. Okay. Now, if some of you are thinking, what about that 1/3, 2/3 business? That's the centroid. That's not what this triangle is. Again, we have the incenter, so it's equidistant from the sides. But yeah, that's the measure there. And that's really basically the second half of 5.1.